Einstein might have agreed. A sound theory needs to make at least one specific prediction. General relativity had made two. One involved an infamous problem of Einstein's era. The orbit of Mercury seems to be slightly wrong, at least according to Newton's law. The observable differences between Newton's and Einstein's version of gravity were negligible, except in circumstances involving the most extreme cases, such as a tiny planet travel close to a gargantuan star. Newton's equation predicted one path for Mercury's orbit. Observation of Mercury revealed another path, and Einstein's equation accounted precisely for the difference. Another prediction involved the effect of gravity on light. A total eclipse of sun would allow astronomers to compare the apparent position of the star near the rim of the darkest sun with their positions if the sun weren't there. According to general relativity, the background starlight should appear to be bent by a certain amount as it skirted the great gravitational grip of the sun. Actually, in Einstein's theory, it's space itself that bends, and light just goes along of the ride. In 1919, the British astronomer Arthur Eddington organized two expeditions to observe the position of the star during the eclipse on May 29th. One expedition to Príncipe, an island off the west coast of Africa, the other to Sobral, a city in northeastern Brazil. The announcement in November 1919 that the result of the experiments seems to validate the theory made both Einstein and general relativity international sensations. Yet Einstein himself downplayed the theory's power to predict tiny observable effect in its influence on physics. Instead, he preferred to emphasize the simplicity of its foundation and its consistency. Its mathematical beauty. Mathematicians tends to agree as the physics, such as Dick's professor at University of Rochester. General relativity's known effect in the universe, an anomaly in the orbit of the planet. The deflection of starlight, we obscured in the extreme, its unknown effect on the history of the universe, cosmology, were speculative in the extreme. Even so, Einstein also acknowledged that if the theory made a prediction that observations contradicted, then, as would be the case with any theory under the standard of scientific method, science should amend or abandon it. By the time Dick joined the Princeton facility in the 1940s, after the war, Einstein was as much as a spectral presence in life as his theory was in experimental physics. Sometimes a seemingly homeless man would shuffle into a facility party, and the younger folks in the crowd would need a moment to recognize the shock of hair and the basset-hound eyes. During the 1954-55 academic year, Dick took a sabbatical leave at Harvard. Then he found himself returning to the thought of general relativity. As a scientist who was equally at ease designing equipment and constructing theories, Dick realized he could do what previous generations couldn't have done with their existing technology. When he returned to Princeton, he resolved to put Einstein to the test. His experiments over the coming years would improve place occulting disk in front of the sun and determine its precise shape, which affects its gravitational influence on the object in the solar system, including Mercury, bouncing laser off the moon and using the round trip time to measure its distance from Earth, which would indicate if its orbit was varying from Einstein's math in the same way the Mercury orbit varied from Newton's math, and using the chemical composition of the star trace their age and evolution, which in turn would be important of tracing the age and evolution of the universe, which in return which in turn will involve an attempt to detect the relic radiation from the primeval atoms. Cosmic fireball, Big Bang, or whatever you want to call it. Dick wondered if a theory of the universe would avoid not only a Big Bang singularity, but the steady state's spontaneous creation of matter, and he proposed a compromise of sort, an oscillating universe.